I'm glad to be here today, and I've missed some of the Hertz gatherings that have been the last couple of years, and look forward to getting back to those with the help of Hertz fellows that are developing vaccines and solving epidemiological problems like we talked about last month. So a little more about myself. I grew up building model airplanes, playing with them, ultimately learning, the math of lift and drag and thrust and so on, like probably so many Hertz fellows. Professionally, after grad school, did a lot of work on consumer electronics, figuring out how to make very sensitive capacitive sensors, scale them up to the hundreds of millions of units that are needed in cell phones, to billions, in fact. And eventually retired from that and went back to my home shop to build more airplanes. But well, my friends that I built airplanes with, gliders, a friend of mine that I built an electric motor glider with, kept asking me for a little help on one thing or another at ZeroAvia. And pretty soon I've become a failed retiree. I've got a job now, and the folks at ZeroAvia really convinced me of their vision for a zero emission aviation system, community, infrastructure. So a little bit about that. The idea is hydrogen electric fuel cell propulsion. And what I want to emphasize is that, especially in the news these days, there's a lot of publicity about electric VTOLs, air taxis, urban air mobility sorts of things. That's not us. Those are all interesting things, but where we see the need is to provide the propulsion system for the aircraft that doesn't create CO2 and ultimately lead to global warming. So in the aviation industry, today, about 5 to 10% of the total global warming is a result of aviation fuels, combustion. And the reason I say 5 to 10% and not a more specific number is because really there's some uncertainty, about a factor of 2 uncertainty in how much of the CO2 and how much of the H2O and particulates emitted by aircraft stay in the upper atmosphere for how long, how much they affect the total infrared radiation from the surface getting back to space, and therefore affecting the net warming of the planet. As ground transportation and ground industries are shifting to more renewable fuels, we don't really have a good alternative for powering aircraft over long distances. And so the present forecasts show that this 5 to 10% of the contribution to CO2 in the atmosphere could become 25 to 50% over the next 30 years. Partly because of increases in aviation, but partly because of decreases in other CO2 contributors. So how do we get around this problem? We've looked at battery electric, turbine hybrid, biofuels, synthetics, hydrogen combustion, and really, other than the hydrogen fuel cell, we don't see a solution to the problem. Battery electric is very heavy. Fundamentally, a battery consists of both the fuel and the oxidizer. When you're burning kerosene or gasoline to fly through the air, 15 kilograms of air is used with each kilogram of fuel. And if you have to take all that oxygen and pack it in the airplane and carry it with you the whole time, all the way to landing, that adds a lot of weight. So just fundamentally, that's why batteries are heavy. There's also a problem of life cycle costs. Batteries don't last for many thousands of cycles unless you only use a fraction of their capacity. But if you use much of their capacity, then their lifetime is short. And in aircraft, because the battery is so heavy and costs energy to fly weight through the air, you pretty much have to use a large fraction of the capacity, and therefore you have short battery life, and therefore the cycle cost in the aircraft is pretty high. Hybrid engines. Hybrid engines make a lot of sense in a Toyota Prius or in a ground vehicle because it's stop and go driving most of the time. You can put momentum into the vehicle and then take it back out and stuff it back into the battery. For aircraft, that's really not the way that's not the way we fly. There's a large continuous power need. And so you have to size the propulsion system, the energy creation, to that average propulsion need, which is very close to the peak power needs. So spinning a generator with a turbine loses 10%, or spinning a generator, storing it in a battery, taking it out of the battery, turning it in, driving an inverter to spin a motor. Altogether, that loses at least 10% of the energy, basically for no benefit. So we don't see a reason to do hybrid in aircraft, at least for long distances. Biofuels, they're a great idea because they take carbon out of the atmosphere. You store the energy as a liquid fuel, very easy to transport, easy to control, but it takes a lot of land to grow the biofuels. They're taking that away from food production. If we did this to any significant scale, we'd be cutting into the world's food supply. And we still have the problem of the carbons and water are deposited at high in the atmosphere where they don't fall out as rain quickly and contribute to global warming again. Synthetic fuels, similar results as far as putting carbon into the atmosphere up high. And it's fundamentally more expensive than hydrogen. When you look at how synthetic fuels are made, you could use electrically renewably powered hydrogen production, combine that with CO2 extracted from the atmosphere. And some of that process is already available through the petrochemical industry at fairly large scales. The petroleum industry has in their refineries quite a lot of hydrogen production, but most of that comes from natural gas cracking with water, or so-called water reformer processes, which ultimately that carbon's going into the atmosphere. The energy source was the methane versus oxygen in the air. So by the time it's converted over to electric renewable sources, it's still a very expensive process. Hydrogen combustion, the nice thing about it is you can use what's very similar to or exactly the same engines that we use today, but there are some material processes that would want to be changed. It is still a very high temperature process. The metallurgy needs to be changed a little bit to avoid hydrogen atoms entering into the metal, swelling the metal and causing it to become brittle. Also, it's a high temperature combustion process, so nitrogen oxides are made. The amount of water deposited in the atmosphere would go up, and the amount of CO2 would go down. Water is also a strong greenhouse gas. Usually, we think of water being in the lower atmosphere, below the tropopause in the troposphere, where weather deposits that water on the ground as rain in fairly short order. But when you deposit a lot of water into the upper atmosphere, it takes a long time for it to basically rejoin the weather cycle. And while that water is in vapor form in the upper atmosphere, it's blocking infrared radiation and contributing as a greenhouse gas. And then fuel cells, we believe, are fundamentally better. You still have water delivered into the upper atmosphere, but less of it because it's a more efficient process. We're also looking at ways to cause that water to fall to the lower atmosphere sooner. So our overall vision is renewable electric energy sources like wind farms and photovoltaics, driving hydrogen electrolyzers to make the hydrogen. That hydrogen can be at the airport. You don't need pipelines and trucks carrying the hydrogen around, which is one of the infrastructure limitations today that makes hydrogen less practical for ground vehicles. Where to support ground vehicles, you might need 500,000 or 50,000 fuel stations around the country. For aircraft, you could probably do it with 500. And a large fraction of the hydrogen would be at let's say the top 100 airports in the country. The hydrogen is loaded onto the aircraft, drives a fuel cell. It's basically an electrochemical combustion process. You combine oxygen in the air with the hydrogen in the fuel to make electricity. The electricity goes through a inverter or motor controller, spins the motors, motor drives the propeller to create thrust. The water and heat goes out the back. Now, there's some momentum for introduction of hydrogen for ground vehicles and for ground energy needs, but really there's quite a bit more momentum in the aviation segment, partly because it has very high energy density, and partly because the alternatives, like I described before, are not very viable. Battery electric is just really not viable for aircraft, and the 5 or 10% improvements you might see in a year aren't even close to getting us there anytime soon. So a number of industry and government agencies are very interested in further developing hydrogen for aviation. So today, we're working on a 2-seat turboprop aircraft shown in the top left. That's a Dornier 228, 2 small turboprop engines with a 19-seat capacity aircraft. In getting to that point, we've flown 2 6-seat aircraft, both of them Piper Malibu or Mirage type aircraft, one in the US and one in the UK. And we've done both United States and UK development, partly because that's where the government funding has supported it, and partly because fundamentally aviation is a very international industry. We have customers and suppliers throughout the world, and to work with them, we don't want to be a single location entity. In the UK, actually where I was and just yesterday, not far from Oxford, Anne, we've got about 40 or 50 people working on the development of a certifiable design for this Dornier aircraft, and also for next stages in the larger aircraft. The 19-seat market is a little bit special for regulatory reasons. There's additional regulations and limitations on the operation of the aircraft as starting at 20 seats. So the FAA's requirements for certifying a 20-seat aircraft are considerably more stringent than a 19-seat aircraft. So we're starting with this this 19-seat version, which is also there's a pretty popular market segment. A lot of the local package carriers and feeder airlines that deliver passengers and packages to hubs use this size of aircraft. That's the Cessna Caravan, the coming Cessna Grand Caravan, Dornier 228 in the bottom right, Pilatus in the left is a single engine. And so it's a good target market for us at this time. It lets us scale up in steps of 3 or 4 and not steps of 10, which are the larger the step in scale up, the more the surprises. And at around 500 miles, it serves a lot of the market. And we believe we can do 500-mile range on this type of aircraft using hydrogen fuels. The next step would be the single aisle, larger turboprops, 50 to 100 seats. And that's the, like in the top left, you see the ATR, actually that's an ATR 72 on the left and an Dash 8 on the right, de Havilland Dash 8. The ATR is a Airbus co-venture with an Italian company. De Havilland of Canada builds the Dash 8, and both of those are 70-ish seats with engines in the 2 megawatt power range. So that's again another 3 or 4 X step up for us in power. Of course, there's a big sticker across the page that's funded, and what we mean by that is we have investment funding in the company sufficient, we believe, to carry us through this stage. And also we have in-kind funding from companies like Alaska Airlines and their subsidiary Horizon to actually provide the aircraft that we're going to use. So they're providing a Dash 8 like the one on the right. And we'll be, we're setting up the hangar to get ready to start work on that plane soon. So it's been in the news a lot. We've got a lot of interest throughout the world and throughout the aviation industry in supporting ZeroAvia to do these projects. And you know, as a scientist engineer, this isn't my focus, but it is a necessary part of the overall development of aviation. We can't just it's not sufficient to design a good product. You also have to sell it. And you have to get it out into the community so that people can recognize it. They can build the infrastructure that supports it. Start training mechanics to work on electric motors, and not just combustion engines, and so on. The whole infrastructure around aviation has to be developed, and we're doing that in part by developing our partners, companies like Shell that are providing fuel. The companies that maintain the aircraft, we've got some partners there. The companies that build and the aircraft or install engines in them they're all desperately interested in this because frankly, they see the writing on the wall. Kerosene is a problem. And they both want to be good citizens, and they want to be seen as good citizens. So that they can maintain their business and their future revenues. Today, this is actually these pictures are from Cranfield. We've actually just moved from this airport in England to a new, a larger airport at Kimball. We're putting up our own photovoltaic arrays to power the on-site electrolysis. These are actual pictures of the systems in operation. This truck in the top right can deliver the hydrogen fuel to the aircraft. And we're trying to practice what we preach too. Our ground vehicles there are hydrogen powered Toyota Mirai. And in the back, you see the hydrogen powered 6-seat Piper Malibu. And this one is partially an artist's conception. This is the Dornier 228 I mentioned earlier. This is the actual paint job on the aircraft now, but the hydrogen tanks under the wings are still fiction. That's Photoshop. At present, this airplane is in the shop. We've taken one turbine engine off of it, and we're putting the electric motor on it now. It'll fly initially with batteries while we test the electric subsystems, the software, the controllers, the motors, the rest of the propulsion system. And also kind of it's not really an afterthought for us, it's an important part of the project, but thermal management and how the motor powers all the other systems in the aircraft. When we take the second turbine off next year, we've got to provide power to all of the other things in the aircraft, the landing gear, the controls, the electronics, the air conditioning. And so all of those subsystems also need to be powered in addition to the propeller itself. On the ground, this is here in Hollister, California. And this test rig, we built that up from a military cargo vehicle. And we did this because it provides a very stable base so that we can spin a big propeller on the top of it and have the thing not blow over. The propeller on this test right here doesn't look so big. This is a 600 kilowatt system. But as we go to 2 and 3 megawatts on the same test rig, that propeller will be about twice the diameter, about 4 meters. This one's about 2 meters diameter. And instead of 600 kilowatts power, it'll be up to about 3 megawatts. The thrust will be in the order of 6,000 to 10,000 pounds thrust. And so this 30,000 pound vehicle will hold it down. It does actually also have hydraulic outriggers, which were part of the crane. And that's one of the reasons I bought this particular vehicle for the system. Keep it stable. It's also so that we can drive this very noisy machine over to the other side of the airport and be away from our neighbors and not annoy them. So everyone, it's natural to think that electric aviation will be quiet and much quieter than engines or piston engines or turbine engines. And those piston engines and turbine engines really are noisy, but the propeller's noisy too. So while this is quieter than a jet engine, it's we're still wearing hearing protectors when we're close to it. And again, I mentioned we're getting a lot of press. These are just some of the publications that have recently published stories about ZeroAvia and about the work we're doing. And again, that's important, not just because it helps us get funding for our company, but also because it develops the whole infrastructure that makes hydrogen electric aviation possible. And government support as well as the commercial support. We've got substantial interest or funding, I should say, from the Aerospace Technology Institute in the UK, which is sort of their equivalent of NASA. We have a substantial amount of US funding as well, based on hydrogen infrastructure, some parts that are in the present infrastructure bill working its way through Congress, and some that's currently funded already. And then on the private investment side, both the companies that are already in the aviation business and see a particular need to transition out of combusting hydrocarbons and into electric or hydrogen power, and also the like the Gates and Bezos funds that are looking at basically save the world from overheating and melting all the glaciers. This is one of the more potentially cost-effective ways to reduce the carbon deposited in the atmosphere today. So with that, I'm going to say thank you on behalf of the investment side of the conversation. Most of the slides up to this point were really aimed at investors and at not very technical people, but we're here with the Hertz Foundation. So I expect that a lot of you have much more technical questions that I haven't answered yet. And I'm going to open it up for questions shortly, but first I'll throw out a couple of categories where I think the questions should probably be centered, or where I expect them to be centered. In this overview of the infrastructure, we see the ground-based energy collection, the hydrogen generation. I've I've really glossed over some things here. This electrolyzer is somewhat complex. It has very strict requirements on the water going in. It has expensive catalysts. It has thermal management and a bunch of other things inside it. It's not just a simple membrane and hydrogen magically comes out on one side after electricity goes in on the other side. Once you make the hydrogen in that electrolyzer, it needs to be either compressed to very high pressure as a gas, and that heat needs to be dissipated, or refrigerated to make liquid hydrogen. Fundamentally, for long-range flight, liquid hydrogen will be a requirement. The fuel tanks to carry gaseous hydrogen at high pressure are heavy. We get somewhat better than 10% gravimetric efficiency. So it takes a 90-pound tank to hold 10 pounds of hydrogen as a gas. And it doesn't really matter much whether it's a big tank at low pressure or a small tank at high pressure. They turn out to weigh about the same. Also glossed over here, the fuel cell. It's at first glance, that fuel cell is just a simple membrane with some catalysts. You put hydrogen on one side and air or oxygen on the other side. The hydrogen is broken down into hydrogen atoms by a catalyst. The hydrogen atoms are ionized, and the electron goes around the circuit through what's the light bulb in this picture, while the proton travels through the membrane to meet an oxygen atom. Again, another catalyst lets the oxygen and the hydrogen combine to make water, and the water exhausts down here at the bottom right. And so as an electrochemical process, that's simple, straightforward, but like so many things, it's not that simple in real life. The proton moving through the catalyst dissipates a lot of the energy. About 40–50% of the energy is deposited as heat in that membrane. The water that's formed on this catalyst, if it covers the catalyst with liquid water, then the air doesn't get to the catalyst. So the reaction more or less shuts down. The hydrogen coming in needs to be uniformly over the catalyst so that the catalyst can stay charged. And so you need but it's being depleted as it moves across these membranes. So you need to recirculate it, control its temperature. The membrane is only going to work well over a narrow temperature range. So we're trying to keep that at let's say 78–80 C, while it's, if we're running say a megawatt of power out of this, of electric power, we're also making about a megawatt of heat. And to remove a megawatt of heat at 80 C is actually a big deal. Requires a very careful and efficient process to move that heat out of the system. A gas turbine is much less efficient, but it makes its heat at 1000 C or 1500 C. So it's very easy to just blow it out the tailpipe and the heat's gone. Here, that's not so simple. A lot of the heat's deposited into the membrane. It's carried away by either the hydrogen or by the depleted oxygen air. It's also, this whole assembly is liquid cooled, and then there's pumps to drive coolants. A lot of the waste heat is deposited directly to the environment or indirectly through pumps and coolants and radiators. And also some of the waste heat goes out as the exhaust. Some of the energy loss also goes in driving the pumps, driving the compressor that brings the oxygen up to the same pressure as the hydrogen. It's another thing I glossed over. This membrane is a thin piece of plastic. So you have to, we want high power density. So we want the hydrogen and oxygen both to be at fairly high pressure so that each piece of catalyst can work on a lot of hydrogen atoms per second. But since both of those are at high pressure, and this is a thin plastic membrane, well, they better be at the same high pressure. or else it's going to blow the membrane apart. So details like that make this simple in concept idea actually complex when it comes down to machinery and controls and pumps and valves and so on. Then, so that's about the fuel cell. There's also everything else. Storing the gas, I mentioned high pressure and liquid hydrogen storage. I mentioned the thermal management. All of these pressures and temperatures are under feedback control. So there's a software loop that's running and controlling valves and heat and pump speeds and things like that. There's a knob in the cockpit that the pilot moves to get more or less power. That directly controls the inverters that drive the motors and also the propeller pitch, but it indirectly controls the fuel cell that makes the electricity that goes to the inverter. And along the way has to power other aircraft systems. And finally, a lot of regulatory requirements to fly an airplane over innocent civilians and carrying innocent civilians. We want to keep them safe. The engineering to keep them safe is one thing, and then the paperwork that convinces people that you kept them safe is a completely other thing. So in the CAA in the UK and with the FAA in the US and other countries, that regulatory system is actually a big deal. So it's a significant fraction of our workload as a company is doing the paperwork that convinces them it's safe for us to fly. So with that, let's open it up to questions. And I'm going to use my prop here. I'm going to have a nice sip of fuel cell exhaust while we bring up those questions.
Excellent. Thank you so much for your presentation, Bob. Our first question will be from Andrew Teal. So Andrew, you can unmute yourself when ready.
I was curious about, in your early slide about alternative ways to power aircraft, comparing versus hybrid and things like that. Is there any hope for solar powered aircraft or nuclear powered aircraft?
Okay, I'll take those two separately. Let's see, I'm going to pull up that slide. So solar powered aircraft. Sunlight gives you sunlight delivers about 1 kilowatt per square meter. To fly one of these sort of regional transport aircraft, we need about 1 megawatt of power. So if you could convert all of the energy in 1,000 square meters to electricity, you'd be there. But we can't really drag 1,000 square meters of wing or of billboard around the sky. And that neglects the 20%-ish efficiency that you get from the solar cells. So it's really 20,000 or 5,000 square meters. And that's just a ridiculously large wing if you put all the solar cells on the wing. Now, that said, I have helped build a solar powered airplane that flew across the country in 1989. It was called the Sunseeker. My friend Eric Raymond built it, and I helped with some of the composite construction and some of the motor and inverter development for that. But in order to make that possible, it needed the very best solar cells, thin film solar cells, I should say, at the time. And it had to be an extremely lightweight aircraft with very marginal strength requirements. So it was a just barely strong enough to fly safely airplane for one person, and it was really a glider. Even using the solar cells on the wing, putting the solar cells on the wing, added drag and weight that slightly better than and the power produced by the solar cells more or less compensated for the added drag and weight, but it didn't make the airplane fly. But Eric, being a very good pilot, managed to fly it in a series of flights from San Diego to Kitty Hawk, North Carolina, and land it there on the anniversary of the Wright brothers flight some 90 years earlier, 85 years earlier. So it's possible. And there have been solar aircraft since then. Some very highly publicized flights around the world with very specialized aircraft that look funny, I'm trying to remember the name of the aircraft right now, but it flew around the world in a series of flights, and particularly to cross the oceans, it needed to fly all night long. So it carried batteries, it charged the batteries. And I mentioned also when I was talking about battery electric that you really have to use the entire capacity of the battery to make it practical to use in an airplane. That airplane used basically 100% of the capacity of the batteries. And as a result, they did have a battery fire and lost a complete battery stack on the ground. Fortunately, it didn't destroy the whole aircraft. But really, you're really operating at the very margins of the technology to make a solar battery electric airplane that can fly. Okay. Your other question was about nuclear. Well, certainly you can get very high nuclear power densities, but you can't put it close to people. If you shield it enough to protect the people, then it becomes very heavy, and then it doesn't fly anymore. So there have been military designs that potentially could have flown. As far as I know, none ever did, because they were just too terrifying. And somebody had the judgment to decide not to do that. Next.
Cool. So the next question is from Mark Cronshaw. So Mark, you're welcome to unmute yourself.
Hello, Bob. Thank you for a great talk. My memory is stretching way back to when I was an undergraduate doing chemical engineering, and somehow, and this might be completely wrong, but maybe you can set me straight, I was under the impression that if you had a large volume of gaseous hydrogen, it was unusually explosive. Is that right, or is that just completely wrong?
So, okay, so everyone remembers the Hindenburg, and what's generally forgotten is that the Hindenburg caught on fire, not because of the hydrogen, but because of the nitrocellulose dope used to coat the skin of the aircraft and to seal it from the hydrogen, to seal it. That was extremely flammable. The hydrogen also burned, but really the gondola on the bottom of the aircraft wasn't damaged by the hydrogen so much as by the fall and by the nitrocellulose covered fabrics all around it. The hydrogen came out through the top and went up and made a big fireball. It's true. Now, hydrogen itself is not flammable. It has to be mixed with air to create a flammable mixture. Now, hydrogen is flammable over a very wide range of mixtures with air. From something like 5% up to 95% hydrogen is actually a flammable mixture. And that's a much wider range than with, say, kerosene, gasoline, propane, even methane. And that's partly because it takes less energy to crack the hydrogen molecule than it does to crack the hydrogen atoms off of a hydrocarbon. And the first step of hydrocarbon combustion is a splitting off one hydrogen to form a radical, and then the rest of the hydrocarbon chain sort of unzips. Now, as a result of that process, hydrocarbons at high pressure and temperature can detonate, which hydrogen doesn't really do. So hydrogen is somewhat more flammable, but less explosive in a way. The key to making a safe aircraft that's powered by hydrogen is to not mix the air with the hydrogen. And even in a fuel cell, they're actually never mixed. In a combustion engine, you would mix them just as they go into the combustor of a turbine or of a piston engine. And that's exactly the same process that's used for combusting gasoline or kerosene. You mix them just as they're going into the combustor. The liquids you'd atomize, a gas is much easier to mix. But fundamentally, the way we keep a hydrogen airplane safe is by not mixing the hydrogen and the air, and by having strong enough containment and potentially barrier areas so that if a leak does happen, it can't reach a concentration that's flammable, and having alarm systems and detection systems that detect the leak, both detect oxygen in getting into the hydrogen side or detect hydrogen getting into the air side of the system. And then if that's detected, valves close and you shut off the flow of the hydrogen. Worst case, you might have to vent a hydrogen tank overboard if the tank itself is compromised. But there are procedures to deal with that, and it's part of the safety procedures we have in place now, and part of the certification procedures we're developing with the government agencies. Thank you. Good question.
All right, I'm going to turn it over to Dana Jean Andrews for the next question.
Okay, I get my turn on. Bob, it was a good presentation.
Thank you.
I'm an old airplane designer, and I'm just curious as how you're going to sell this when a hydrogen-powered turbine engine is going to be a lot lighter and cheaper.
Range.
Range?
Range. We can fly about 50% farther using hydrogen fuel cells because the fuel cell is much more efficient than the turbine.
That's true. It's twice, should be about twice.
Right. And because hydrogen fuel tanks are big, they're bulky. I don't think I really mentioned that, but hydrogen is very low density. And so redesigning the aircraft to accommodate the size of the fuel tank is kind of a big deal. And you don't want to commit that much space in your airplane to fuel if you could make it smaller. So a smaller fuel tank providing greater range, we think is the selling point in new aircraft. In existing aircraft, which is really the target market we're going after right now, because you as an aircraft designer will understand this. The lifetime of airplanes in the transport market is around 30 years, right? There's still 747s flying that were built in the early 70s. And the vast majority of airplanes flying today were not built this year or last year. They were built sometime in the past. And if we want to make a dent in the carbon flowing into the atmosphere anytime soon, we need to be able to convert existing aircraft, and we need to also accommodate the new production. But we're mainly going after the STC or supplemental type certificate method of converting an existing aircraft to hydrogen fuel cell propulsion.
Congratulations. That's an excellent answer.
Oh, thank you. We did put some thought into it. And funny, your voice actually sounds very much like a friend of mine, Mike Friend, who designed the first hydrogen fuel cell aircraft at Boeing. And he's on our advisory board.
I spent 30 years at Boeing and was designing a hydrogen airplane 50 years ago, which never got built.
Right. You may know Mike Friend if you were at Boeing around the same time.
I remember him.
Yep. Thank you.
You bet.
Excellent. Let's turn it over to Tony Pan for the next question.
Hi, Bob. Nice to see you again. This is
Hi,
awesome. Yeah, I'm calling from Max's room, but this is Tony. Yeah, agree. Super cool. Not much other solution out there to decarbonize flight. Could you just talk a bit more about how to store hydrogen on the plane? As you've already noted, hydrogen notoriously low volumetric energy density, bulky tanks. If you compress it, the fuel is like 5 to 10% of the tank weight. Just really hard problem. Just tell us more about how that's being solved.
Well, so first on that number, 5 to 10%, we're getting 13 for compressed gas. But you're absolutely right. Even when compressed or liquefied, liquid hydrogen is only 0.07 specific gravity. And it's if you're used to thinking of water or gasoline or something like that in a tank, and you have an idea in your mind of how it sloshes around, liquid hydrogen is not like that. It's a very different material. Your intuition about liquids in a tank is probably wrong. And that's actually something that's been very important to rocket designers. They blew up a lot of rockets because the hydrogen supply to the engine was interrupted during takeoff. And it suddenly went oxygen rich, and then it surged hydrogen rich, and then boom, they blew up the rocket. So having learned from all of the rocket development, which again is very sensitive to weight, certainly we can do much higher gravimetric density with liquid hydrogen. And for long ranges, liquid hydrogen is a necessity. For up to about 500 miles, there's a trade-off where gas or liquid are possible. And it comes down to cost and aircraft design and the facilities available on the ground. And in particular, whether you need to store the fuel for a long time. If you can put high pressure gas in a tank and close the valve and walk away for a year and come back and it's the same as it was. If you walk away for a year or a month with liquid hydrogen, some of it is gone, maybe all of it, depending on how much insulation you can afford and how well you can insulate it, the size of the tank. If you can fuel the aircraft and then immediately take off, there's very little loss due to boil off, due to refrigeration requirements. There is a lot of loss when you first fuel a warm tank. So you might think, well, you could pre-refrigerate the tank with liquid hydrogen or with liquid nitrogen or something like that, and then but you still have to cool from about 77 Kelvin down to 11 Kelvin using hydrogen as the refrigerant. So that feeds into the aircraft design. There needs to be a way for that boil off to safely escape, possibly to be recovered and re-refrigerated, or just to be exhausted into the atmosphere or used to power other things. As for where to put the fuel in the airplane, Boeing and several others have concluded that long, thin tanks mounted on the top of the fuselage are the most effective design. And the reasons for that are, one, you want it outside of the pressure vessel where you store people. If there is a leak, you want to vent it to atmosphere, not to inside the airplane. Aerodynamically, changing the cross-section of the fuselage is a very small penalty in the overall range of the aircraft and the flight performance and the controls. When Boeing built the Skylifter, I'm forgetting the exact name, basically is cylindrical fuselage 747 with a huge tube on top, much bigger than the original pressure tube. It actually was done also as a supplemental type certificate. It did not require the pilots to undergo any new training. The airplane flew pretty much the same as the original. And that's the tool they use to transport 787 fuselages across the ocean. I think a lot of those are built in Japan and then delivered to Everett, Washington for assembly. And so basically liquid hydrogen on top is our primary target.
Excellent. Let's turn over to Andrew Teal again for another question.
Thank you for giving me another turn. But I don't think any of my questions remaining are very important. I'd rather give somebody else a turn. Thank you.
Okay, let's turn it over to Michael Floyd. And just a quick note that Bob mentioned that he would be available for a short time after the hour as well, if people have additional questions.
Hey, great talk, Bob.
Thank you, Mike.
Really interesting concept. My question concerns the scariest part of your slide deck, which was the truck full of hydrogen pulling up next to the airplane.
Mm-hmm.
And so my question was about, well, how do you safely get, first of all, how big a bomb is that, and how do you get it from where you make it to the airplane and load it safely, considering the total energy that's in that truck?
Well, so two parts of that is, would you consider a truck full of gasoline a bomb?
Yes, but the one that doesn't quite explode with the drama potentially of hydrogen. So I've never seen a truck full of hydrogen explode. So I'm not quite sure what.
Right.
It looks scary, but how scary is it?
Well, so if there were an explosion itself, if you had high pressure tanks that you put a shaped charge on it and ruptured the whole tank at the same time, it would break windows. It would be loud, and the pressure pulse itself would hurt things. Then you'd have hydrogen suddenly mixed with air, and if it were ignited, it would burn, but that it's so buoyant that it would very quickly rise away from the ground and do relatively little damage on the ground. Gasoline or kerosene, when it burns, it lays on the ground, and people and things tend to be on top of the ground, and they get burned up. So if the fireball is above you and going up, it's not nearly as scary as when it's in a puddle underneath you. And I should say that I'm a active, pyrotechnic. I do a lot of actually very large scale pyrotechnic shows, and I'm much more scared of liquid fuels than gaseous fuels. So yeah, there's in liquid hydrogen, there's a special hazard with liquid hydrogen in that if you suddenly pour a lot of liquid hydrogen on the ground, for example, on asphalt, the air above it gets supercooled. You start freezing liquid oxygen out of the air. The liquid oxygen falls on the creosote or asphalt in the pavement, and that starts to burn. So the hydrogen there is actually as a refrigerant causing the hazard, not so much because of its own fuel value.
Okay, let's turn it over to David Tuckerman for a question.
Hi, Bob. Great presentation. So when you mentioned, 80 degrees C of waste heat in the megawatt range, I was thinking, well, can you turn that into an anti-icing or de-icing system for all the surfaces and sort of solve your heat transfer problem at the same time that way?
I'll say yes, and not comment on it very much because not all the patents are filed. But we're looking at every way we can think of to use the heat that's produced to supply needs throughout the aircraft and on the ground. If you imagine a whole bunch of subsystems as boxes, and there's an arrow going from any box to any other box, then the arrow represents heat. We're looking at what could you do with that, and evaporating liquid hydrogen so you can use it as a gas is one thing, and you use the cold storage of the liquid hydrogen to cool things that are hot, and you use that waste heat to evaporate the hydrogen so you can use it. And basically every possible arrow on that subsystem diagram is something we're looking at. And, and this is a good time to mention that, you know, Hertz Fellows are the kind of people we'd like to hire. And if you have an interest in solving some of these problems along with us, please contact me after the presentation. My email address is on the top slide and should be available through the Hertz Foundation, or I can give it to you again.
Thanks.
All right, I'm going to turn it over to Brian. This will be the last moderated question, and then after that, we can open it up to more informal Q&A format.
Okay, yeah, again, thanks, great talk. I had a bunch of questions that you answered before I even had a chance to ask them, so it was really, really great. One thing I'm curious about is you know, what's the kind of current like timeline or status of the fuel cell development? How do your R&D fuel cells compare to, and how do also, you know, existing commercial fuel cells compare to the final targets that you actually need for like a viable aviation product? And, and it kind of relates to the question, like in commercial aviation, there's all the specialization, right? Like you get turbines from Rolls-Royce, and you have all these different companies, like, you know, like, so I guess it's connected to like, you know, should fuel cells be coming from like one company that just does fuel cells? Yeah. So
there are many existing commercial fuel cell suppliers, and we've looked at you know, pretty much all of them we can find. Generally, the fuel cells that are on the market today as a commercial product are designed for ground use. They're designed for buses or heavy trucks or mine equipment or something like that, where weight is not a major penalty. And generally, those are designed in rectangular boxes, and airplanes don't have a lot of rectangles in them. They're also heavy, and airplanes don't like heavy. So to adapt the existing low temperature polymer proton exchange membrane type fuel cell to our uses, we're making it lighter and making the balance of plant, the compressors and regulators and things that fit around the fuel cell smaller and lighter. Another aspect is called high temperature proton exchange membranes, and the relatively high temperature, meaning over 100 C. So high temperature fuel cells use basically new polymers that are being developed for the purpose. The heat flux is a little bit different because you start at a higher temperature. It makes it a little easier to move the heat. You can use less coolant and less air moving through the system to carry the heat away. And all of those make it probably more suitable for use on an airplane. So we're working very hard on that direction of development. There's also an area that we're not working on so much, and that's say ceramic membrane fuel cells that operate at much higher temperatures, but they transport carbon atoms as well as hydrogen atoms. And there, methanol or methane or propane can be the fuel source, and the catalysts crack the hydrogen or the fuel into hydrogen and carbon. They both get transported through the membrane, and they both get recombined at the other side. Now, electrochemically, that's not super efficient because the carbon-oxygen bond isn't at the same electrochemical voltage as the hydrogen-oxygen bond. So, and not all carbon-oxygen bonds are equivalent, where basically hydrogen-oxygen bonds are pretty much all the same. So there's some inefficiencies, but it operates at a much higher temperature, but it's still a carbon source. So you would be dumping your carbon dioxide in the upper atmosphere again. So that's not really an area that interests us. So the high temperature and low temperature proton exchange membrane type fuel cells are where we're doing our work. Does that answer the question?
Yeah, thanks. I mean, I guess maybe the related part, I mean, is okay, if this kind of unique approach to, like, you know, fuel cell development is such a key thing, like, okay, what's this gets maybe more just like a business and economic question. You know, should just focusing on like the fuel cells be like one whole mission of its own, separate from, you know, building an airframe and you know, motors and everything around it?
Absolutely.
Yeah.
The fuel cell is a small part of a big problem, but in itself, it's still a big problem.
Yeah.
None of this is easy, and none of the fuel cells developed for running a data center or a bus really serve our needs.
Great. Yeah, great. Thanks. Fantastic answers. Yeah.
Okay. So, Alex, do you want to?
Yeah.
I know you.
Yeah, I just wanted to say thank you for presenting today. We all really learned a lot, and I really appreciate your ability to address questions about so many different areas in this field. Has been really fantastic. I think now we can transform, or we can sort of go to a more free-form format. If people have any other questions, people are also welcome to sort of head out or whatever they see fit. Yeah.
Yeah, I'd be happy to hear people's feedback or comments that aren't necessarily questions that I can answer, but you know, maybe questions that I can't possibly answer, or statements about the state of the world and how this fits into it. I'm open to hearing the other viewpoints that are out there.
You know, how much more expensive would jet fuel have to be, or how much more expensive would like an airplane ticket have to be on a conventional aircraft plane before like a hydrogen plane made sense,
right?
Or became preferable, you know?
So I believe, okay, I'm gonna sidestep.
How much quote worse is a hydrogen powered plane than a conventional one, if you ignore all those externalities?
Right. So ignoring the externalities, it's possible to build a hydrogen airplane using technology that we know about that is cost competitive directly. Now that assumes that we have hydrogen hydrolyzers that we can build at a, you know, sort of industrial scale and industrial cost basis. And it assumes we continue to make renewable electric sources at a what's presently already cost competitive rate, right? You mentioned at what gasoline price is a electric car competitive? And the answer is we're already there.
Right, for cars, we're already there. Yeah.
Cars are already there. Okay. That's done. How much further does it have to go to support airplanes? Right. And the answer is, it isn't actually about the cost of the kerosene or the cost of the hydrogen. The hydrogen airplane will be much cheaper to maintain in some ways because it doesn't have a high temperature combustion process and doesn't have a 20,000 RPM turbine that's trying to throw its blades out at high temperature. Those hot cores of those engines have a finite lifetime and a scheduled replacement time, and it's expensive. Those are multi-million-dollar engines that get replaced on a few-year cycle at the most when they're in frequent use, and that amortization of that capital cost is easily competed with by motors that last much longer. So the airplane itself, it will be more expensive to make a liquid hydrogen tank than a kerosene tank. Kerosene tank's just an aluminum box, you know, with a hole on the top and some holes in the side where pipes connect to it. It's really simple. A liquid hydrogen tank is generally going to be a very lightweight composite structure with very advanced insulations, likely aerogels and things like that to support the inner structure and to prevent punctures and be strong enough to survive crashes. So that's a much more expensive fuel tank. The systems supporting the fuel cell are bigger and somewhat more complex in some ways than turbine engines. But turbine engines aren't simple. There's if you look at the cross-section picture of a turbine, it's pretty simple. You squirt fuel in here, it burns, it blows out there, and things spin. But if you actually look at a real turbine engine on a real airplane, you go, what is this 100 pipes for? Why are there thousands of wires? Why are there little tubes all over the place? And the answer is it's trying to be optimized over a range of conditions means there's valves that open and bypass some systems and close for some operating conditions, and tries to be efficient operating at cruise power and also still have enough peak power for takeoff and climb. And similarly, on a fuel cell, you have to be able to operate over a range of conditions, which means different external air pressure is a big one, and external air temperatures. So you need to be able to compress air up to your operating pressure of the fuel cell and then release that pressure in an efficient way. And so there's the fuel cell itself is a small part of the fuel cell system. And there are costs there. There's a few sort of not easily mitigated costs, like the catalyst in the fuel cell stack itself. Palladium and platinum are expensive metals, no doubt about it. But they're not that expensive compared to single crystal nickel turbine blades. So we think we can actually have direct cost comparison that favors the hydrogen airplane in the next 10 or 15 years.
Great, thanks.
This is Mark Cronshaw again. I have a couple of comments. Thanks for inviting that. I really support your idea of a carbon tax, but it's a huge political problem, unfortunately.
Sure. Absolutely.
The other thing is, over the course of my career, I've been surprised at some things that businesses have done. For example, in the early 1980s, I spent a while doing financial analyses of a proposed gas pipeline from Prudhoe Bay in Alaska to the lower 48. And a total of $600 million was spent on studies for that pipeline when it was really clear from the outset that it was not going to be economical. And I'm afraid some of the ideas that are being proposed for reducing carbon emissions are also similarly not sensible, like direct air capture. Why on earth would you try and extract a really low concentration of carbon dioxide? It's peculiar to me that these things go on.
Right, I agree completely. It's baffling.
But by contrast, I think your approach seems really well suited for purpose. I'm really impressed by your talk. Thank you.
Thank you. Thank you. Well, a lot of those economic studies were a part of forming the idea and the vision of this company. We looked in depth at a lot of other ways of reducing carbon impact and selected aviation as a place where we could make a difference. We looked at a lot of aviation alternatives and selected hydrogen fuel cells as the place where we could make the most difference. And yeah, we don't want to build a pipeline from Prudhoe Bay. That's just crazy. And actually, we don't want to build hydrogen pipelines either. We want to, if you need to transport the energy from one place to another, do it as electricity and hydrolyze near the consumption.
Bob, I have a question about the idea of sort of real-time generation of the hydrogen fuel on at the airport is really appealing. And so a couple questions. One is, I know I don't think they're in common use, but it's possible to make electrolyzers that create the hydrogen at high pressure to begin with, avoiding the need for compression.
Right.
Is that a factor in your planning? And the second question is, have you looked at kind of the power budget that's needed to sustain a major airport? And is it a realistic number, or do you need like a gigawatt substation there to keep the electrolyzers going at the rate they're needed?
Right. Great question. One advantage of hydrolyzing in the first place is hydrogen storage on the ground is cheap and easy. You can have a really big tank at a low pressure, and it's not that costly. So you don't have to have real-time production of hydrogen. You just have to have it, over the previous week, supply this week's hydrogen, or some time scale like that, maybe week to week or day to day averaging at the least. And that means if you plant a whole bunch of solar cells all over your electric grid, and they're massively overproducing during the afternoon or in the middle of the day, this gives you a power sink that lets you make use of that. We've seen, especially in West Texas, the basically electricity prices going negative because the air turbines are creating more electricity than there's any demand for. And in Australia went negative a few times in the last month, producing more electricity than they knew what to do with solar. And this is a great way to put the lowest cost excess electricity to work. Now, that said, hydrolysis and fuel cells are not as efficient as a lot of other energy storage mechanisms. So it does not make sense to replace hydroelectric pumping and dams with hydrogen fuel cells. The hydrolysis process is in the 50–60% efficiency range, and the fuel cell operating at its desired operating conditions are around 50 or 60%. And together that's 30% or so round trip energy efficiency. It's not great, but it provides the energy density you need on an airplane. Yeah, so that's why I think hydrogen fuel cells are a good alternative for airplanes, even though I don't think they're a great choice for cars or buses or even trains, because the battery is more efficient. You can use a heavy battery and operate it in a long lifetime mode. You don't have to use all, more than 80% of its capacity. And so you can get many thousands of cycles out of the battery. So I think maybe aviation isn't unique, but aviation is certainly an area where you need the portable energy density that you can get from hydrogen or from liquid hydrocarbon fuels, and we don't have any alternative to those.
Yeah, that makes a lot of sense. Thanks.
Yeah. David, one other thing. If you want to use peak solar and wind power to make hydrogen, you also need to install hydrolyzers that are bigger than they need to be on average. So there is a cost to that, which is hydrolyzers that run, say, 4 hours a day instead of all day at a lower power. And so there is a higher capital cost to trying to efficiently use the grid's excess power.
Right.
Like to, as Alex said in the chat, Bob, as he had to go, Alex had to go to another meeting. I'm going to close up, and I'm delighted that so many folks, we still have 11 folks on the call, staying this long after the hour to chat. I think we had a really great conversation, and you also may not have seen, Bob, that lots of people thanked you for your great presentation in the chat as they left. So I'll do that again, and thank you so much for both the amazing presentation and staying almost equally as long to answer questions afterwards.
Thank you. Yeah, thank you everyone for the great questions. And again, my email's up there on the screen. If you have an interest in contributing to where ZeroAvia is going, please let me know. Or if you just have more questions, I'm happy to answer them.
Great. Thanks so much, Bob. Thanks everybody for being here.
Thanks, everyone.
See you next time.